Good afternoon. Are there any admin or logistics questions? So the admin and logistics kinds of things that I know you have are, there's exam on Friday. Bring your computers because it's all going to be computing. And I'll give you a heads up that it will be hard to give much partial credit on this upcoming exam. It's just the nature of it. You're going to compute a number, it'll be right or wrong. And I will not be able to proctor it. I'm giving a presentation to the Board of Trustees. I was the co-chair of the Commission on Academic Freedom and Freedom of Expression. We're running a half-day retreat for the trustees on Friday morning. But I will be around a great Friday afternoon. Yeah. Yeah, so office hours kind of thing. If anybody wants to talk about academic freedom of expression, that's been my thing for the last 2 years. On the homework, show of hands, how many people have received from Solver a message to the effect of, this problem is too big for me, Solver, to be able to handle it? 1. Okay. And 2. Have you two already talked? Are you the second person Justin was mentioning to me who got that message?
No.
No? Okay. So it obviously isn't happening to very many of you, but it is happening to some. Justin has come and talked to me already. I don't know what's going on. The handcuffed version of Solver should be able to handle 200 blue cells. And I don't know why you're getting that message. And I really don't understand why, which problems are you getting it for?
Number 3.
That's the max flow problem?
Yeah.
Yeah, and it makes no sense to me at all that it would show up for the max flow problem and not the others. So at the moment, I'm just totally puzzled. So I'll just acknowledge that I know that's happened to 2 out of 50 of you, and I don't have a solution at this point.
I got that when I did it wrong.
When you did it wrong, what was wrong, and then what did you fix?
I put like the 999 in the wrong spot. I think I put it like, I included it as a note. Does that make sense? Like we have to make a big note.
I mean, I hear what you
Made a note.
and then you
Said it was too big.
fixed that and it changed. You're very
I just
interested.
don't know how much to give
Do
away.
you want to repeat?
Yeah, so what I did wrong was I made like a fake node when I didn't need to. And I put the like infinite supply in that area. And then it told me that it was way too big of a problem to handle, but I don't think I was supposed to do that anyway. Like I put
Yeah.
the
I still don't
999 in the
understand
wrong
why
spots in different
you
places.
got that message from that. Do you still have your wrong version of the spreadsheet, or do you think you've got
And I
one?
deleted it. But I did get, I know when I put the 999 in a few wrong spots, it was telling me that it was too big to handle.
I got the same issue too. I got that first. It said it wouldn't, it was too large to run Solver, and then I changed it.
And was your original spreadsheet error similar to that?
I don't remember what my error was, but I remember seeing it, and then I changed something, and then it went away. Yeah, I don't have the old version
But I
either.
would think you're putting the not, like the infinite supply in a wrong spot. I would think.
Listen, all right, sort of enough on that, 'cause we got to do the other stuff too. So you all know everything I know at this point about that. All right, and no other admin or logistics questions, any substantive questions? All right, so you all had to watch that asynchronous lecture before coming to this lecture. Chapter 6 is by far the hardest chapter of the mini. So that is, gives us the chance to slow down and spend more time on problems. But I do want to kind of check that you guys understood what you needed to understand out of that lecture you watched before coming here. So I'd like you to pair up right now, and one of you explain to the other the meaning of this relationship, where it comes from, and what the implications are when you're running an integer programming problem, and then switch, and the other one explain why it is that you should start the branch and bound algorithm with blue cells, obviously the technical term being decision variables, that are feasible and at least pretty good in terms of performance on the objective function. Right? Being able to answer those two questions shows that you understand what you need to understand about the branching bound algorithm. So take 4 minutes in pairs, one person explain, A explain to B the thing on the left, and then B explain to A the thing on the right.
Okay, so
Yeah, we've been.
I start with a low tolerance. As a value which is between A and C. For example, I have 100 in some value. Up here I have value, and I get this one. Essentially, I should be going down this line even further down. So what I do is if I have 5% solvent, essentially
Get a frame of
And like there's a bunch of like lines.
And you never press yes. People high tolerance and run
Yeah, so your boundary will have will have like strings that are
I'm going to give you the time switch. You're halfway through your time.
yeah, but like a bunch of dogs.
Did you like it?
Yeah, I see. It's easy. A lot of reading. I had
Okay, so that's time. I'll ask you guys to articulate that in just a second, but real quick, the backdrop for those statements is the branch and bound algorithm, which branches and then likes to bound. More specifically, it's a recursive algorithm that looks at an IP and says, I don't know how to solve that, so I'll solve its LP relaxation instead. If the optimal solution to the LP relaxation is integer, it says, hooray, I'm done. Because the performance on the LP relaxation is always at least as good as it is on the original IP. So if you get the optimal solution, the LP and its integer, you know you're done. If the solution to the LP relaxation is not all integer, it picks some variable and forks off two daughter subproblems, one adding a constraint, that variable is less than or equal to the round down, the other adding the constraint that it's greater than or equal to round up, and then solves both of those. That works because all feasible solutions to the original problem are either on the left side or the right side. So if you find the best on the left and the best on the right, you found the best overall. The bad news is that tree can become ginormous, to use a technical term, very quickly, even if the problem isn't all that big. And so we like to bound or chop off branches whenever we get the chance. Right, so that's the background for it. So this graph, first of all, what's the vertical axis mean? That's an easy question.
Time taken.
Computational.
Just how long it takes the computer before the computer says, I'm done. Horizontal axis is
how much like suboptimal, how okay you are, how flexible you are with the solution if it's suboptimal. For like example, if it's 5% suboptimal, then that's your tolerance, right? You're okay with settling for a little less than perfection.
Yep, absolutely. Perfectionist, laid back Southern California surfer dude. Why is this relationship decreasing?
Because it's less computation, increase the tolerance.
That is a true statement, but why is it we get to do less computation when we're more laid back?
We don't go into that many branches anymore. Like we stop.
We can prune more aggressively. Yeah, when we're looking at the score on the LP relaxation, which is a bound for the best possible solution value underneath that node, sometimes we look at it and say, well, I might be able to do a little bit better than my incumbent is the term solution, i.e. the integer solution that's feasible and I have in hand already. But if you can only do a wee little bit better by doing all the work to check out underneath it, you may not bother. And so the less bothered you are by an amount of suboptimality, the more aggressively you can prune. How about this one? Why does that help branch and bound? Yeah, John?
When you accept a pretty good solution, you can improve your frame of reference from which you can further increase your optimality.
All true, but connected to, I can start with blue cells that are feasible and pretty good, or I can start with blue cells that are infeasible. Why is it better to start with blue cells that are feasible and pretty good? Yeah.
We reduce the model population by limiting the bound of the blue cell values.
Well, all true, but there's something very specific, which is you can start bounding right from the get-go. You cannot start to bound until you have a solution that's feasible and integer valued. And this means you can start bounding right from the beginning. If the initial solution is not feasible, then solver's going to have to go all the way down that tree, branch, 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 until it finds a feasible solution to be that candidate that allows it to begin bounding. Until you've got a feasible solution, you've got no basis for trimming any of the branches.
Yeah, so I guess then why would you say that you could start with an infeasible solution? Is that
You shouldn't.
because you
I mean,
slow
you
down?
could, but that's being cruel. because it forces branch and bound to do nothing but branching until it stumbles on a feasible solution.
So you technically could do it, it's just not.
It's just going to be slower. But if we start it with something that lets it bound right from the beginning, it will tend to do better.
So when you're saying feasible solution, which is pretty good, does it also include an LP relaxed solution? Can we start from that? Is that considered?
No, because, well, if the LP relax solution happened to be integer value,
Yes.
but if the solution is not integer, then it's not feasible to the original IP. So you're going to type in blue cells that are all integer and which satisfy all the constraints, and you kind of give your best common sense judgment of what you're going to do. Like you would follow some heuristic, you would do some common sense thing. So the solution's not too bad. It may be not optimal. It's too much to expect a human to find an optimal solution. But if you can do that, that's being nice to your computer.
So how do we find the feasible pretty good? Do we join the high tolerance thing?
No, I'm saying even before, I mean, so there's two, yes, it is a good idea to successively cut the tolerance, but I'm saying before you even run it the first time, if you have the ability to prime it with a feasible solution, it's pretty good, you should. And so we'll look at it when we get to examples. So I'll hold that thought until we get to the examples. All right, and examples is the name of the game. The whole point of doing that flipped classroom stuff is so we can spend more time talking about the problem types. And as I briefly alluded to in that video that you watched, we have genuinely 4 new problem types, but we also have 4 kinds of things that can show up in any problem that we want to be able to handle, things like fixed costs. And the lecture on this stuff you'll watch for Thursday. We're going to start to roll through these and also be able to work the cases on Tuesday and Thursday, which is good because we don't have recitation. All right, so we start with employee scheduling. Employee scheduling is not the same as the assignment problem. It's easy to mix the two up. What we're doing in employee scheduling is deciding how many people will be assigned to work each shift from amongst a large pool of identical and interchangeable people. So the context for this are things like scheduling police officers, scheduling nurses, large number of people. You're trying to figure out how many will work. It's not trying to figure out when will Sally work and when will Jim work. And this is only interesting if the number of people you need varies over time, but that's a pretty common situation. And when you dig down and say, what exactly are we deciding in this problem? It's how many people will be assigned each shift, where the word shift has a meaning that's specific to this problem that's a little bit different than the way we use it in everyday English. Right? So in everyday English, we think of a shift as just indicating kind of, are you working day or night? Are you working 9 to 5? That's the day shift. Are you working the graveyard shift from 11 to 7? Here, when we use the term shift, we mean more than that. We mean everything you need to know in order to know exactly whether that person is working or not at all possible times. So it may mean not only knowing that they work 9 to 5, but knowing that they work Sunday to Friday. So you have to specify which days they're working as well as the times that they are working. And for every distinct possible answer to that, you've got a separate decision variable. And the constraints come from the different moments in time. So you slice up the day or the week, or in extreme versions like scheduling surgeons, you can go even further out in the future than that. And you take that total time horizon and slice it up into chunks and say, for each of those chunks of time, the number of people working has to be greater than or equal to the number of people you need to have working to achieve adequate customer service or meet safety standards or whatever. And then your objective is to minimize the cost of doing that. Best learned by example. I have an example in the slides for scheduling police. I'm not going to talk about it because it's there in the slides. You can read it. What we'll do right now is the Snooker's restaurant problem, because I mean, the name is just intrinsically funny. So we got to use Snooker's case. Snooker's is a restaurant. They're open from 8 to 10. They also need to have somebody on staff an hour before they open and an hour after. So we actually are scheduling from 7 a.m. to 11 p.m., even though the customers are only there 8 a.m. to 10 p.m. We have two categories of workers: people who work an 8-hour shift and people who work a 4-hour shift. And if you look at the numbers, you'll see that the full-time workers get paid $10 an hour. The part-time workers get paid less, $8 an hour. And the actual wages are old. Ragsdale has not updated his parameters and his problems since he wrote the textbook quite a while ago.
What year was that?
That's a good question. He was the person who really kind of revolutionized the whole way management science is taught. He was the first person with a modern spreadsheet-based class. I think I started teaching this course in 2000 or 99 maybe, and it was a couple years old at that time. So it would have been like mid-90s. Before then, the classes were entirely different and basically were entirely math classes, all theorems and so on. Anyhow, the restaurant is also divided the day up into 7 blocks of time. And you can see up there on the screen how many workers are needed in each of those blocks of time. 7 blocks of time, so we'll get 7 constraints from that. The one thing I don't like about this problem, and I want to sort of warn ahead of time, is this problem has 7 different shifts, so it'll have 7 decision variables, and it has 7 blocks of time, so there's 7 constraints. It is sheer coincidence that those are the same. There's nothing that says that the number of shifts and hence decision variables need be the same as the number of time blocks and hence the number of constraints. Could be bigger, could be smaller. It's just coincidence. And then the additional twists down here are we must have at least 1 full-time worker in that very opening time and very closing time. And during the crunch time, we want at least 30% of the employees to be full-time workers. I think the idea there is that it's sort of hectic and you want some experienced people around, not just enough bodies, but enough people with experience. Any questions about the problem that Snookers is trying to solve? Cool. I think the way to teach this one is to start just showing you the spreadsheet, and then we'll talk through why it works and also what the algebraic formulation would look like. All right, so this is oriented so that there's a row for each shift and hence each decision variable.
You meant to add the last 7.
It doesn't really matter because I'm just priming it with some numbers, but thank you. And the columns corresponding to those time blocks that have the requirements. And what you need to create is this block of yellow, which is not binary decision variables. They're not blue. You're not letting solver choose these, but these indicate whether somebody who is hired to work this shift is or is not present during this block of time. So the first row is pretty easy. People who are hired to work from 7 to 11, they're there from 7 to 11, and they're not there for any of the other times. People who are hired to work from 11 to 3, they cover the time slot 11 to 1, and they cover or help out with a time slot from 1 to 3, but not the other time slots. I've sorted these decision variables to put the full-time workers down towards the bottom. This shift represents people who work an 8-hour shift starting at 11 a.m. So they're there from 11 to 1, 11 to 3, 11 to 5, 5 to 7. So that row has 4 ones in it corresponding to those 4 blocks of time. Questions about that?
Yes.
Yep.
So the X1, X2, these are employees or?
The X's are decision variables indicating how many employees will be assigned to work that shift. So the current solution says 1 person will work part-time from 7 to 11. 4 people will work part-time from 7 p.m. to 11 p.m. 9 people will be hired to work an 8-hour shift from 3 to 11. And then the yellow ones and zeros just indicate if somebody is hired to that shift, will they help meet the demand for workers in that time slot? So yellow cell IJ is 1 if people hired to work shift I are present at time J. And that's just yellow. That's just a fact. Let me just do one more to talk it through. If you are hired to work from 7 a.m. to 3 p.m., are you going to be on the job from 7 a.m. to 11 a.m.? Yes. Yep, so that's a 1. Will you be there from 11 a.m. to 1 p.m.? And from 1 to 3? Yep. Are you still there from 3 to 5? No. So we're just translating the times into yes, no, are you helping to meet the demand for workers at that time slot?
That was correct.
The row 10 is some product of that column of indicators with the blue cells. It adds up how many people are actually working at that time. So this current solution is not feasible because it does not have enough people working in the first part of the day. And actually, it's also short in the late afternoon and the dinner time rush too. So we'll, in a minute, let Solver give us an optimal solution. Down here, I've got those other constraints. One is just the number of full-time workers who are working at that very beginning must be at least 1. So some product now only over rows 7 and 9 because only decision variables 5, 6, and 7 are full-time workers. So that's going to have to be bigger than 1, and then there's another one at the end of the day. The most complicated constraint is this blending type constraint. At least 30% of the workers must be full-time workers. If I have 13 workers and 30% must be full-time, that means 3.9 must be full-time. Likewise, in the dinner rush, if I have 18 workers and 30% must be full-time, I must have 5.4. This cell is the number of full-time workers during the lunchtime crush. This is the number of full-time workers during the dinner time crush. So this must be greater than or equal to that. This must be greater than or equal to that. All right. Oh, I didn't tell you the objective function yet. Objective function is min cost. So I'd like to come up with the least costly way of staffing my restaurant by choosing the ideal numbers of people to work all of those shifts, subject to the constraint that in every single one of these time periods, the number of people working is greater than or equal to the number that I need. That's like the core employee scheduling constraint. This problem, and many of them will have other additional constraints, and I'm entering those now. Right? And if I run Solver, here is my optimal solution. How many people should I hire to work that 4-hour shift starting at 7 a.m.? Like 9 living people and a torso. And in the next time slot, it's 16 living people plus a decapitated person. So I am not only not going to work at your restaurant, I don't think I'm going to eat at your restaurant, but I appreciate the enthusiasm. So this is why we need to be able to add inequality constraints. As a quick aside, if all of your constraints just look like that, it's actually pretty common for the solution to just fall out being integer. So the LP relaxation can get you an integer solution in a pure scheduling problem, but it's these blending constraints that are really what's causing the non-integrality. So now we're going to go back and add as an additional constraint that these decision variables must be int for integer. There is no right-hand side. You just choose the comparator to be int. XL fills in integer. I can keep the solution algorithm in this bottom box as simplex. Solver is smart enough that when there are integer decision variables, it knows it's going to do branch and bound. Telling it simplex here says when you're solving the relaxation, as you do many times during the branch and bound, you're allowed to use simplex on the relaxations. We should come over here and make sure some things are checked appropriately. First of all, if the ignore integer constraints box is checked, you're not going to get an integer solution. So you want that to be unchecked. Then the really important ones are the tolerance parameter. That's that horizontal axis. And these limits on running time. Make sure the limits on running time are present so that the computer will check in with you before it goes and runs forever. This is a not huge problem, so it won't take forever, even if I start off insisting on full optimality. I didn't look at it. Presumably the cost went up when I added the inequality constraint, because whenever you add a constraint, you can't possibly do any better. Did anybody notice what the solution was a second ago? Solution value? I'm sure it was not lower than 2512. Question back here? Yep.
So integer optimality is our tolerance?
Exactly. That box is that tolerance parameter. So had this been a full-size scheduling problem with 100 or 200 or 300 decision variables, I would have started that out with 10 for 10% or something like that. Computers are so fast these days that 7 integer variables, it just still solves. And that's a change. When I started, when Ragsdale first wrote this problem and we were solving this 15 years ago or whatever, you would notice it would take the computer a little bit longer to solve. Now you can't see the difference. You had a question?
Yeah, so the constraint precision in the solver dialog box, that's by default set to 0. So at the top.
You know, a month ago, I would have very confidently said, never mess with any of these other options that I don't talk about. But now that Erica found out that you can fix that other problem by messing with them, I'm slightly less confident in saying that. When problems get large, then it becomes important to tune these parameters, but tuning them well depends on knowing what the algorithm is doing at a level beyond what we do in this class. So it's not constructive for you to have to mess with those. I hope it's true that for the rest of the semester, we don't need to talk about them.
Yeah.
But so in the real world, you're going to confront kind of 2 kinds of optimization problems. Ones that are small and you just solve them and it works out pretty well. And then ones that are big, and then you have somebody on your team who didn't just take one course of management science, they got a degree in management science, and you'll be the boss and you'll tell them, you figure that out. All right, all good on employee scheduling problems? Excellent. Yeah.
I guess this is a follow-up question. With the time iteration and the we don't mess up with that either, right? Sounds like it.
Like I said, until very recently, I would have just said the defaults always work. So, oh, I'm sorry. No, you're talking about these two?
Yeah.
Oh, no. These you do really want to think about. They are both limits on how long the computer will work before it checks in with you.
Right.
And you do not want to write in for max seconds 87 billion. So you're going to use 10 or 20 or 30 or something like that seconds that it will run. And if the problem is a big and hard problem, it literally will run that number of seconds, and then it'll flash off this little message that says, haven't been able to satisfy you yet. Do you want me to keep going? And that's when you never, ever press yes. That's when you say, no, don't trick me. And then you'll go back and before rerunning it, increase the tolerance or find a better initial solution or something like that. So yeah, the three boxes that you do care about are these guys. And as a practical matter, I almost always control it by seconds, but you can control how long it runs indirectly with the iterations side. All right.
Yes.
Oh yeah.
So in the context of exams, how many seconds would you say you should limit it at?
So the good news is you will never run an IP on your computer in an exam because this Friday only covers through chapter 5, and your final exam will be back to being a pencil and paper exam. The final exam is going to very heavily emphasize writing formulations, including all the integer programs, but it'll be handwritten. All right, so the next problem type we're coming up to is the capital budgeting problems, which is a very important problem type, but we're going to squeeze in a special case of the capital budgeting problem called the knapsack problem, because it only takes a few minutes. And the knapsack problem makes an interesting point when we look at it. And it's one of those things where if you're in a job interview and you say, hey, I've taken an analytics course, they could quiz you on this. It's such a classic problem that if you want to present yourself as someone who knows this field, you should have heard about this problem. The origin of the problem is somebody wants to go backpacking and they want to bring with them lots of stuff. They want to bring food and a canteen and an axe and an air mattress and a tent and whatever else, but it doesn't all fit into their knapsack. And so you have to make choices as to what you're going to bring. Everything you could bring has some value, and your objective is to maximize the value of the things you bring with you, but there's a capacity constraint on your knapsack. And you can either think about it as a weight constraint or a volume constraint, but to be a knapsack problem in the mathematical sense, there's just one constraint. In fact, a mathematical definition of a knapsack problem is a binary integer programming problem with just one constraint. And I will illustrate an application of it, quote unquote, to the sort of real world. Suppose you're a funding agency. I call it to the National Science Foundation in this case. You've got $250,000 with which you can fund applicants. You have more applicants than you're able to fund, so you have to make choices. You have an assessment of the value to society that would be created by funding each of these projects. That literally comes from having your friendly faculty members spend a weekend eating bagels in Washington, DC, scoring these proposals. We do that. That's your objective function. And the key idea in all knapsack problems is you are not allowed to partially fund things. Going back to the camping knapsack problem, You cannot take half of an air mattress. It doesn't produce any value for you to take only part of it. And the idea here is likewise with the scientific project, if you only give half the funding, they'll get the experiment set up, but they won't have time to actually run the experiment. You'll generate no value. So the decisions are yes, no, will I fund it or not? And I've set this one up where I've rank ordered the projects in terms of their benefit cost ratio. So the first project produces 20 points worth of value for society and is a $40,000 budget. So the ratio is 0.5 on down to project 6, which has the lowest benefit cost ratio. So what you might be inclined to do is say, let's just march down that rank ordered list, funding projects and decreasing benefit cost ratio until we run out of money. And we'll see how that works. You already know the answer because I've cooked the books. I always do. So if we fund the first project, we will have used up 40,000 of our $250,000 budget. We've got 210 left over. That's plenty to fund the second project. So we fund the second project. Now the amount of money that we're spending is the 40 plus 50. We've still got $160,000 left. So we fund number 3. We've got enough money to fund number 4. Now we've got $40,000 left. We cannot fund these, so we stop. And we will have generated 92 points worth of scientific progress to help society. That is what's called a greedy algorithm. It's a common sense heuristic, but it will not turn out, in this case, to produce the optimal solution. We can solve this to optimality as an optimization problem where we maximize the value created by choosing the right value for those 6 binary decision variables, subject to our one and only one constraint that we have to not exceed the budget. Well, it's one and only, plus in addition, we have to specify that those blue cells are bin for binary. So not only integer, those are yes, no binary decision variables. This is now a very small problem, so it solves very quickly, and it shows you could score 105, not just 92, if you forego funding project number 4, because that allows you to fund both projects 5 and 6. They are less efficient than product number 4, but you're nevertheless able to do better overall. And sort of the punchline here is, even with this extremely simple integer programming problem where the decision variables are binary and there's only one constraint, it's in some sense hard to solve. A greedy heuristic can get trapped and not find the optimal solution. So mathematicians like this because it's hard even though it's so simple. And that generates the conceptual idea that we really are in a more difficult situation when we're in chapter 6 than we were before. Yep.
Is this a binary situation of previous fund allocation problem?
When you say previous allocation problem, are you thinking of the Blacksburg Bank allocation problem?
Yeah, we have a problem where it's like.
So I guess the short answer is, yeah, they are kind of related because you've got a pool of resources that you're spreading out. That problem's the Blacksburg Bank problem, the focus was on minimizing risk by spreading stuff around. Here, we aren't thinking about risk per se, but yeah, they're related. All right, any questions? Yep.
So when you do the bin constraint, do you like no longer have to go into options to ensure that?
No, I still have to do that. The only reason I didn't this time is that's a really, really small problem. It's only 6 variables. They all have to be binary. So there's literally only 2 raised to the 6th power or 64 possible solutions.
Okay.
If you had a pure binary problem with 1,000 decision variables, 2 to the 1,000 is a very big number. So it can absolutely be necessary to constrain the running time of a binary problem. It's just this itty bitty.
Okay.
All right, all good. So that is what it is, and it's sort of a preamble to the more general class of problems that are called capital budgeting problems. And capital budgeting problems mathematically are just knapsack problems with more constraints. So the key decision you're making is you're making go, no-go decisions on a large number of projects or endeavors, and you don't have the resources to do them all. So you have to pick. And all of them have an objective function coefficient that's sort of how much happiness, value, goodness you would get if you funded that thing. But then you have multiple constraints. Why do we call it a capital budgeting problem? Because the classic application is the one described in the book. It's capital investments or investments in capital things, meaning buildings and stuff like that. And when you do something like build a building, that creates cost consequences, not just today when you pay to build it, but year in and year out after that. You have to maintain it, you have to run the HVAC system. And typically you aren't going to just have a building with no people in it, you're probably going to have some employees in it. So the decision to build it today not only bumps up against the budget constraint you have today, but it has implications for the budgets in the out years. So in this particular problem, the way you read it is that the NPV column has already factored in all of these costs. It's the net present value, it's the profit. So that's what we're maximizing. But all of these 6 projects have cost implications each year over a 5-year time horizon. And we have to stay within budget in all 5 of those years. And it may well be that there are 2 projects that are individually great, but they both place great cost pressure in the same time period, and then you might not want to go with both of them. That's the origin of the name. What sector of the economy has to wrestle with capital budgeting problems of this sort more often? Government or for-profit, and why?
Government.
Correct, because?
I mean, sorry, because when it comes to government, for certain projects, it could allocate certain resources. And a lot of times legislation could complicate certain things. So that's why bureaucracy, red tape, certain things can slow down. And then if a politician is out of office, someone takes over and wants to cancel the project.
So this is all true, but you're starting to digress into general cynicism about the government sector. Yes, but it's a more concrete thing. Governments often have difficulty moving money across time periods. If a certain amount of money is appropriated to be spent in this fiscal year, it's all got to be spent in this fiscal year. Whereas in the private sector, if you were ever in the situation where you would say, boy, we could do super amazingly well, but we're just pinched in year 3, but we've got plenty of excess money in years 2 and 4, Wall Street is happy to come in and help you figure out how to move money across time periods through financing. But it is common that government is more constrained in its ability to use extra resources in one time period and shift them into another time period. Okay, so that's what a capital budgeting problem is, but they do not always manifest in terms of budgets in different time periods. All of you will face a capital budgeting problem in almost exactly 12 months in your capstone project class. Not for the client, but in the internal management of your own project, because you and your 6 fellow students will by February 14th have about 100 great ideas for things that you could do that would create value for the client. But you will only at this point have about 10 weeks left. And if you think 7 students times 10 weeks times 15 hours a week or whatever, that's a finite budget on how many things that you can do. And it is often the case that you don't want to do something halfway. It would be better to do one thing well than 4 things halfway. So you're going to have to make these concrete decisions. We're going to fish or cut bait, we're going to do it or not. And you're going to, at this point in the semester, have to decide, no, this might be fun to do, but we just aren't going to do it. We're going to put all our energy into the things that we actually are going to be able to finish. I've advised a fair number of systems projects over the years, and I have pushed all of them to be very explicit at around this time of the course to make that list and use the presentation to the client, the first one, to get some sense of how much they would value each of these things. And I push them to make a serious guess as to how hard it would be to do each of the things, understanding that there's a fair amount of uncertainty there. I don't normally expect people to literally then put the parameters into Solver. Usually it just becomes a good way for the 7 students to have the conversation about what are we going to do or not do. I did have one class one year where the project manager literally ran the thing in Excel. But I like to give you that example that you're all going to face capital budgeting problem, point out often there's a lot of value in just being able to understand the structure of a problem and then use the language and terminology to communicate with people about it, even if you don't press return and get your solution by computing. So anyway, the example that we're going to do is video games, because it illustrates this idea that the constraints are not always money in different time periods. So a video game software developer has 7 proposals for new games. The company kind of developed all of them because the budget is limited in terms of dollars and also programmers. So 2 constrained resources, capital budgeting, not knapsack. In addition, projects 2 and 6 require the same specialized programming knowledge, and only one of the programmers has that. So you can't do both of those. So what should we do? That's a capital budgeting problem. Every one of the 7 things that we can do or not do gets a column and an associated binary decision variable. So if I were to consider this solution, that would mean we do projects 2, 3, and 4. That would produce for us 1,600 units of value. It would use up all of the programmers because 6 plus 9 plus 5 is 20. It would not use up all of the capital because 175 plus 300 plus 150 is less than the 950 we have available. It would satisfy this constraint that x3 plus x6 must be less than or equal to 1. So that constraint about the specialized programmer gets written x2 plus x6. Yeah, sorry, 2. Suppose we tried to do both projects 2 and project 6, which coded with these decision variables would mean x2 is 1 and x6 is 1. The left-hand side would be 1 plus 1. That would violate this constraint. That constraint would allow us to do project 2, but not project 6. 1 plus 0 meets the constraint. It would allow us to do 6, but not 2. It would allow us to do neither of them. 0 plus 0 is less than or equal to 1, but it precludes trying to do both projects 2 and 6 simultaneously. Any questions about how the spreadsheet works?
Is the equation x2 plus x6 less than 1 is that a mathematical way to basically write that to constrain that both projects are kind of redundant, like and related or similar to each other, so you should do only one of those?
It absolutely is a mathematical way of saying you should not do more than one. It's not that the projects are redundant, it's the projects share a common resource, this one miracle programmer, of whom we only have one. So the projects 2 and 6 could be totally different, but they both require that one person, and we only have one of that one person. So at the abstract level, as a manager, what are our constrained resources? Money, total number of programmers, and geniuses. And that third constraint is the constraint on we've only got one genius.
Does the specialized programmer also count towards the total programmer?
I have always interpreted the question to be properly modeled the way that it is. So I guess the way I think about it is project 2 requires 6 people, including the genius. Project number 6 requires 4 people, including the genius. But if you always make your model match the real world. The good thing about working in the real world is you can always go ask that question of whoever it is who's the team lead or whatever. Okay, just show you the steps with the solver again. Maximize NPV by choosing the right values of that subject to these resource constraints and also the constraint that these, well, let me leave the binary thing off again for a minute. If we just solve it like this, so I was expecting it to be fractional. In fact, if I show more digits, no, it didn't turn out to be fractional, but it's not allowed to do 2 copies of the same thing. You can't invent the same thing twice. So we have to add the constraint that those decision variables are bin for binary. They are indicator variables indicating yes, no, will we do that project or not? And if we optimize, we can do better than that score that I had up originally, which was only 1,600. And it says do projects 1, 6, and 7. And that meets all the constraints. Take 3 minutes to write the algebraic formulation of this. Fine with me if you use summation notation or not. And I'll make sure you can do the algebra of it.
On the final, would you be using summation notation?
Yeah, I will expect that by then you have mastered it. See, that brings you great joy.
Yeah, I just often hire 2 cases.
Yeah, what for each project?
Oh, really? I'm sorry.
No, don't be. It's okay.
I up until I met with you, I assumed I was doing something wrong.
Well, I'm confused. You still doesn't sound like you found an error. You just.
Oh, I didn't find an error, no. I just, I tried to, first I did a smaller max flow and it worked. So I was like, in a new sheet, so I was like, maybe it was about the new sheet.
I really have no idea why that.
It must be the way I checked it the first time. Which is getting close with my final version.
Oh, that happened with me too. But once, like the Excel got corrupted or something that the solver wasn't giving. Oh no, I was I don't know the context, but I was doing the first homework or something. So it wasn't working at all. Like even though I was putting in all the right information, and it wasn't even like working when I was tracking and putting the formula, I was tracking it down. So I just had to like get rid of the Excel.
Yeah. Yeah, I'm gonna do it. That's how I'll do it. Okay, so always start with your receiving variables. Let xi be binary decision variables indicating whether to do or fund project I. The objective is to maximize the value that's created, which means summing over I, the xi's pre-multiplied by the yellow numbers in row 5, and I don't know, VI, I guess. And in your homework, and even on exam, you want to make sure we know what VI is, where VI is the yellow cells in row 5, the value of doing project I. Then you've got 3 resource constraints. So subject to sum over I, xi pre-multiplied by, and now we need a name for programmers. So I'll use PI for programmers, less than or equal to 20. And you say where PI equals number of programmers needed to do project I. And there's a sum over I pre-multiplying these indicator variables by the amount of capital. I haven't used C yet, so I'll do CI less than or equal to 950. Bless you, where CI is equal to the thousands of dollars needed to do project I. And then the last constraint is honestly easier to do without the summation notation. It's just what we had up before, x2 plus x6 less than or equal to 1. You could, if you wanted to write it with summation notation, have it be something like sum over I g sub I x sub I, where g sub I equals 1 if you need that genius to do project I. And it is good form to say at the bottom xi binary, and there's a whole bunch of ways you can write that. One is to say xi is an element of the set 0, 1, or you can just say where the xi are binary. If you've at the top specified let xi be binary decision variables, technically you don't have to put it at the bottom also, but it's kind of good form. That's the style in which we tend to write formulations. Question? Yep.
Do we have to specify anywhere that it's a range between 1 to 170?
Oh yeah, I should have. So to do project I, yeah, right up here, I should have specified the range of the index. Thanks. Where are we on time? We have 15 minutes left. Not getting to cases, but that's okay.
Quick question. In this case, the capital is like the amount of money we had to spend?
Correct. Yeah, actually, a little farther behind than where I want it to be. Okay, next one is set covering. Set covering problems are very common, especially in the location context. You have customers in a bunch of places. Every customer or group of customers generates a constraint that they must be covered by your service facility. That's why they're called set covering problems. And your decisions are yes, no, will I put a facility in location I? Sometimes the locations the facility can go are the same as the places where the people are, like they're just neighborhoods, a facility in the neighborhood or not. Sometimes the places you can put the facility are literally specific buildings and street addresses, and the places where the customers are don't match directly. So they don't have to, but in this particular problem in the lecture notes, they do. And so we're making a binary decision for each location. And there's this matrix we create of yes, no, is it covered from that spot based on often travel time. So this particular problem was set up to be if the facility is in 3 minutes drive, that's close enough. So if you are sitting in neighborhood 2, you feel like your need for service is covered if there's a facility built in your neighborhood or in neighborhood 3 or in neighborhood 4. All 3 of those would let that ambulance say, get to you quickly enough. But if there's a facility built in neighborhood 5, you're going to die of that heart attack. That 8-minute travel time is too far. So from the perspective of somebody who lives in neighborhood 2, I must have a facility in neighborhood 2, 3, or 4. And so that translates into a constraint that looks like this. Either X2 or X3 or X4 has to be a 1 to make sure I'm covered. So you have 1 constraint for each set of customers that we're trying to serve, 1 decision rule for each place where we could put things. The problem that we'll do is couched in terms of healthcare because HCPM students get ripped off. There aren't. Management science is very useful for healthcare, but Ragfield doesn't have a lot of examples. So even though healthcare system of Florida is a boring name, we'll do this one so that we have problems that are health related. Yeah, so the basic story is there's 5 places we can build facilities and the costs vary by facility. It's the bottom row of the table. And those X's just indicate, would that facility be close enough to those people in order for those people to feel like they have been adequately taken care of? So, oh, I shouldn't have arrested. Still let XI. So let XI be binary. Decision variables indicating whether to build a facility at site I, and now I runs from 1 to 5. And we, in this problem, are obligated to cover everybody, but we want to do that at the least possible cost. It's $450,000 if we build facility 1. So that enters the objective function as 450 times X1. If the X1 is 0, this piece of the cost gets zeroed out. If we build the facility, we pay the 450 plus 650 X2 plus 550, 500, and 525. What is the constraint that will make the people in region 1 happy? That's the good part of the case, because now we have some fun names. The people in region 1 will only be happy if we build something in Sanford or Apopka or both. So how do we do that in mathematical symbols?
X1 plus X3.
X1 plus X3 greater than or equal to 1. And the people in region 2, they're pretty easy to please. X1 plus X2 plus X4 plus X5 greater than or equal to 1. Any one of those 4 facilities takes care of them. People in region 3, it must be X2 or X4. People in region 4 need a facility in location 3 or 5. Region 5, it's 1 or 2. Region 6 is 3 and 5 again. And you can say, do I have to write that again? And it's like, no, mathematically you don't, but typically you set this up so that if somebody later on futzes with the X's, it automatically updates. So it's good form to leave it in. And then the last region requires a facility in either Castleberry or Maitland. So that's the algebra. And this is the this is what the spreadsheet looks like. The Xi's are going to be binary. That sum product is that objective function. And then there's a constraint for every region. We demand that there be at least one facility built within reach of them. And coverage is the number of facilities built that are close enough to help those folks. I've already got it set up. So blue binary, column F bigger than column G, and we should build in Sanford. And I'm so happy we're going to build something in Apopka. That's where I want to go. Questions about this specific set covering problem? They can get big very easily. If there are 60 different addresses where you could build a facility, and instead of lumping your customers into just 7 regions, you divide the state up into zip codes or census tracts, the problem can get large. This also is sort of a general modeling approach. They're not all going to look exactly like this. Sometimes the problem, so this is what's the least costly way to serve everybody. But it could also be phrased as what are the most people we could serve while only building 3 facilities, or the most people we could serve while spending no more than $1 million building facilities. There are instances in which one region might require double coverage, and that's easy enough to handle. The most complicated ones are ones where you end up having to have binary variables, yes, no, is the location covered? So we absolutely are always going to have the binary variable build or don't build, but sometimes you need a second set of binary variables, one for each region. It's yes, no, is that region covered or not? It's a very important class of problems. All right, the last of these problem types is discussed in Ragsdale's book as line balancing. Line balancing is what it sounds like, assembly lines in a factory. You want to have the same amount of work on every line, so there's not one line that is a bottleneck that holds back the production of the finished product. You're not going to run factories, so I don't want you necessarily to spend much time reading that section of the book, but you are going to face a lot of instances in which you care about balancing outcomes for different groups. It's basically an equity kind of thing. And there are a bunch of different tricks for how to do this, but I'll show you now one of these problems. And what we do next week will also give you some more ideas of ways of doing these. So I don't think I have this one open yet. Give me a second to find the line balancing problem. Or so I shouldn't say line balancing. It's a balancing problem, but not a line balancing problem. All right, so Ragsdale's problems of this sort are very often phrased in this sort of way. You have a certain number of customers who have a rating called sales potential, and you're going to allocate them to 5 salespeople. And this is going to be a one-to-one matching. You don't want 2 different salespeople chasing the same customer because you want to present the customers with a single point of contact for the organization. And you got to figure out which customers to assign to which salespeople so that all the salespeople have about the same shot of making sales and making their commission quotas. So who should take care of which person? Right, does that make sense as a problem? And it isn't just in sales. When I've had people in the course who worked in development, it is exactly what we do. So these different big potential donors, they're all rated. You know, we expect to write $1,000 check to the university. We think you might write 100,000. We're looking at you to write a $10 million check. And the different development officers who are going to get promoted or fired based on how much money they bring in want to all be given a fair shot at meeting their quotas. So anyway, when I've had development people in this class, they're like, oh, this is fantastic. This is exactly what we do. So it's not only in sales. What are the decision variables that we have in this problem?
Assign each one.
So we don't get to actually choose the sales potential. If we could choose the sales potential, we'd choose them all to be $1 trillion.
The customer will assign each salesperson.
Yep, that's what we have to decide. And so what's the notation we should use for our decision variables? How many subscripts? 2. Yeah, this is a double subscripted problem. It's a little bit like a transportation problem. Xij is 1 if customer I is assigned to salesperson J, or vice versa. It actually doesn't matter which way you do the indices, but the point is that the Xij's are going to create a connection between a customer and a salesperson. And they're binary because we don't want multiple salespeople interacting with a single customer. And in this transportation problem framework, I guess I'll go to the spreadsheet so we have that to look at. Ignore right now this part. That's the equity part. We'll get there in a second. I've got a row for each salesperson. I've got a column for each customer. This rectangle of blue is going to get filled in with binary values. This solution that I'm typing in right now says salesperson A gets customers 1 and 6. Salesperson B gets customers 2 and 7. If we add vertically, we get the number of salespeople to whom a customer is assigned. That we're just going to force to be 1. We don't just add across the row. We sum product with the sales potential, and then these numbers are the potentials for that those 5 sales reps are receiving. And what we would like to do is to make all of those be 210. Right? Why 210? Just if I add up the total amount of sales potential, it's 1,050. We have 5 salespeople. So a perfectly balanced distribution would make those all be 210. We're not maximizing sales potential. Sales potential is fixed, it's given. Every one of these people will get assigned to a salesperson. What we're trying to do is minimize inequity. And we'll pick up on Thursday because I'm out of time with how to do that. But the hint is that's what's going on in those far right-hand columns with the underage and the overage, and we'll get to that on Thursday.